Questions about anything from before break? I hope everybody had a good one. After break, we're going to start working on the Fourier transform, which is an exciting thing. We'll have a totally different flavor than Fourier series, but they're related to each other in key ways. Historically, I think the first place you might run into one of these transforms that are so useful, like the Fourier transform, usually the first one you run into is called the Laplace transform. It's useful for solving ordinary differential equations. And the engineers love it because it turns solving circuits and problems in vibration into just a routine. And so I thought I'd spend some time motivating what we're going to do with the Fourier transform by doing this classic thing called the Laplace transform. So Laplace transform it's useful for solving ordinary differential equations. So useful, especially of a certain kind the engineers love. How many people have been exposed to the Laplace transform? Okay, that's good. Yeah, almost every. So you don't have to have seen it, but if you have seen it, then this is going to make more sense to you, maybe. It's useful for solving ordinary differential equations, especially initial value problems. And in fact, that's why the integral is from 0 to infinity. The initial value problems at t equals 0. I like to think of t as time if you're going to solve problems in mechanics or engineering. Okay, so and here's the big facts that make this useful. Okay, we're going to write Laplace transform of f of t is equal to this function f of s given by that integral. And it's interesting that we only care about the value of f of s for big A. So notice it, if that was an e to the minus at and a were big, then that would be a really small thing. That would die away really fast. And so we would think that integral would become very quickly convergent for big S. And it turns out that only the tail end of that function is relevant when it comes to applications to differential equations. So usually a Laplace transform will say that f of s is valid for s bigger than something. And the a could be different depending on what the function is. Okay, so we're going to write it like that. The big facts that this is a linear operator. That's obvious because if you had f1 plus f2 and stuck it in that integral, you'd get capital F1 plus capital F2 that were transforms of those two things. So it's a linear operator. And also you can pull out constants. That's nice to know. It's just because integrals are a linear operation. Okay, let's call that fact number 1. Fact number 2 is if you take the Laplace transform of the derivative of something, and this is a biggie, so Laplace transform of f is capital F. The Laplace transform of f prime is s times f of s. And let's see, and the initial value problem comes in here minus the value of little f at 0. So that's exciting because that means the Laplace transform is going to turn differential equations into algebra, equations. That's a big deal. And the Fourier transform is going to have similar properties. And so, of course, you can do that again. So if you do it again, you get the Laplace transform of f double prime. Let's see, I'll figure it out. That would be S times the Laplace transform of f prime minus, let's see, when I had an f prime, this was minus f of 0. When I have a double prime, it would be minus f prime at 0. Okay, and now I have the formula for f prime above, and so I can put that in. That would be s squared. So two derivatives multiplies by s squared. And let's see, that'd be minus f of 0 times s minus f prime at 0. Okay, let me show you why 2 is true. It's not a hard thing to see. Why 2? Let's see. The Laplace transform of f prime would be the integral from 0 to infinity of f prime of t e to the minus st dt. And you stare at that for a second and realize, I can use integration by parts, hopefully. Of course, that stands for the limit as b goes to infinity of the integral from 0 to b. Let me rewrite this as f prime of t dt. That's kind of a big hint. And here we'd have an e to the minus st. So let's call this u, and let's call this dv. Then du would be, let's see, the s acts like a constant in this integral. So du would be minus s e to the minus st dt. And v would be the antiderivative of f prime, so that would be f. Not f. It would be f. f of t. And so the basic calculation of integration by parts tells you that this is the limit as b goes to infinity of, let's see, u times v. So that would be u is, so v is f, I guess I should write it out. Okay, u times v is f of, don't count it, sorry. U is e to the minus s of t, v is f of t. And we're going to go between 0 and b. And then we'll have minus integral from 0 to b of v du. V is f of t. Du is minus s e to the minus st dt. And notice there's a minus s there. That's going to come out in front. So this one's going to be a snap. This is going to give me, when I pull that s out, it's going to be minus a minus. So that would be a plus s times the integral from 0 to b. And there it is. That's the Laplace transform going to pop out when b goes to infinity. So that's where the s times f of s comes from. And this one, let's see. This is where you realize, I better have something about f to make that first thing manageable. And so, in fact, when you look at that, think about the most reasonable thing you can think about for f, and you'll come up with the idea that you need f to be of exponential type. It just means it doesn't grow any faster than an exponential function. Exponential type. Meaning that, let's see, it means that f of t should be less than or equal to some constant times e to the kt. For some m and some k. Okay, if that's the case, then that what would that first term be? Let's see. That first term would go to 0 because of the e to the minus st, when s is bigger than the k. So, let's see, when I stick that in, I would get 0. I let the limit b go to infinity, I'd get a big fat 0. And let's see, in order to get that 0, I would need s to be bigger than the k. Because then I get e to the minus st times e to the kt. That would be e to something negative t altogether. It'd be minus the quantity s minus k, and that's negative. So that would go to 0. Okay, and then we'd have minus sticking in t equals 0, and e to the 0 is 1, so that's where the f of 0 comes from. And then this other thing, as b goes to infinity, is plus s times f of s. So that's how you'd show that, and that's when you realize, oh, I better have some conditions on f. Being of exponential type is pretty hairy. You know, it's way less than being just bounded. Or you know, continuous, etc. So in fact, to make that whole thing work, I would need f exponential type and piecewise C1, for example, would be enough. So in fact, let's see, when I was deciding what else I need to do this, to do integration by parts, I would need f to be C1 smooth. So I see, when I think about how do I get away with all this stuff, I also need f C1 smooth on 0 to infinity. Okay, so those are biggies. Let's see. I think I'm up to number 4. It's a fact, interesting fact, that we can undo the Laplace transform. And so the fact is, that's exciting. We're going to hit a differential equation of Laplace transform and turn it into algebra. And then we're going to solve for the capital F of s. And then we're going to undo the Laplace transform to get the solution to the original ODE. That's the classic approach. So the reason that you can undo the Laplace transform is because if two functions have the same Laplace transform, for big S, for S bigger than something, for some n, m, then they're the same function. On 0 infinity. That means the inverse of the Laplace transform is well defined. And that's what makes it a useful thing. And the funny thing is, to really understand that properly, the best way to do that is to use the Fourier transform and the Fourier inversion theorem. So if you look for a serious book that demonstrates this fact, you've got to do the Fourier transform. So consequently, the inverse Laplace transform makes sense. Okay, I think it's fun to do an example of why engineers love this thing so much. So a classic second order constant coefficient ODE, let's do y double prime plus 5y prime plus 6y equals something, e to the minus 4t. Okay, that's an ODE, and let's say y at time 0 is something, and y prime at time 0 is something. That's a initial value problem. Okay, this could represent, for example, a vibrating mass spring thing. So let's say I'd have a spring here and a mass, the mass m, spring constant k, and a coefficient of friction. Let's see here. In this problem, m would be 1, k would be 6, m is equal to 1, and c, a coefficient of friction, since it's scraping along this floor right here, coefficient of friction, the drag, in other words, that would be 5. And e to the minus 4t is an external force. So think of a stick on top of this thing and a force acting on it. Let's say make this the positive y direction. And there would be this F of t, which is a force, external force, equal e to the minus 4t. That's an external force. Okay, that's the physical problem where this kind of ODE comes up. Or another place where it comes up is an RLC circuit. So let's see, you could have a resistor, an inductor. You can tell I was an engineering student, and a capacitor. And here's an external voltage, E of t. Let's see, is that true? I think so. This is a resistor, inductor, capacitor. And getting the the current in that, if you add up the voltage drops and use Kirchhoff's laws, you would get that differential equation. I won't dwell on where these things come up, but the engineers solve both those problems on a daily basis, at least in school. And so what happens when you hit it with the Laplace transform? hit the ODE with the Laplace transform, let's see, that the y double prime would give me an s squared y of s minus s times y prime at 0 minus, is that what it was? No, it's s times y of 0 minus y prime of 0. That's the Laplace transform of the second derivative. And notice the initial conditions pop in there in a key way. And then the next one would be plus, and it's a linear thing, so it would be 5 times Laplace transform of y prime would be s times y of s minus y of 0. And then finally, plus 6 times the Laplace transform of s, of y, which is capital Y of s. And that would be equal to the Laplace transform of e to the minus 4t. And that's an easy thing to calculate. It's equal to 1 over s plus 4. You just write down that integral and do it. Okay. And notice now we have an algebra problem. We get, let me get it here. We get, look, I can factor out the y of s here and get y of s times s squared. Notice that that's the quadratic thing, that the ODE, the characteristic polynomial of the ODE, second order ODE with constant coefficients. And now I can put everything else on the other side. So let's see, what was my y of 0? My y of 0 is 2. My y prime of 0 is 3. And I got another 2 here. And so when I put those things on the other side, I would get 2s plus 3, let's see, (2s plus 3 plus 10). So that'd be plus 13. Plus 1 over s plus 4. So now I can solve for my Laplace transform and get that the Laplace transform is 2s plus 13 divided by this quadratic thing plus 1 over s plus 4 times this quadratic thing. And if this was a class in ODEs, we'd spend time doing partial fractions and breaking those into little pieces that we could recognize the inverse transform of. Let's see. So you get a y of t when you undo. So apply the inverse transform. You get y of t. From this one, this is the solution to the homogeneous. This is going to be a solution to the homogeneous problem. And it's going to look like a e to the minus 2t plus b. I don't know what those are, but I could figure out what they are. So that's the transient solution. Solution to the homo. And this, let's see, I'm sorry. Oh, blast.
This is going to lead to a solution to the a particular solution. To the ODE. So this is going to be a C1 and a C2 kind of thing. Which, would, by the way, the C1 and the C2 would be determined by this procedure. So it would solve the initial value problem. Okay. Let's see, just to show you how it feels. Okay, let's do the case with 0 initial conditions. Y of 0 equals 0 and y prime of 0 equals 0. Then you get the Laplace transform of my solution, capital Y of S, would only be that stuff, this stuff on the right, 1 over S plus 4, and S squared plus 5S plus 6 is S plus 2 times S plus 3. And you do partial fractions and get that that's equal to A over S plus 2 plus B over S plus 3 plus C over S plus 4. And then when you undo those Laplace transforms, you get little y of t equals A times e to the minus 2t plus B e to the minus 3t plus C e to the minus 4t. And these would be homogeneous solution and this would be a particular solution. In fact, you could use undetermined coefficients if you didn't like to use Laplace transform.
And so it's just it gives you a procedure for solving these problems. I guess that's kind of ho-hum because you also learn how to solve that by standard means. Using the undetermined coefficients to get a particular solution, et cetera, and solving the homogeneous is a routine thing. We've done it when we were solving the vibrating string problem. So that's a routine thing to do. But an exciting thing is that this is particularly useful to engineers if the functions are piecewise defined. It works great. For piecewise defined functions that come up in engineering. So you never convince an engineer that it's not a fantastic thing because of that fact. Anyway, that's kind of motivation for why we're going to do the Fourier transform. It has many similar features. It turns partial differential equations sometimes into algebra. So let's see I said I didn't write. Do I have space to write it up here? Okay, I forgot to write something. So it's a great tool. L, the Laplace transform, takes ODEs and sends it into algebra. Then you solve the algebra.
for the capital Y of S, and then you undo the Laplace transform. You get the solution. Y of t is the inverse Laplace transform of Y of S.
Okay. Well, we're going to do something similar with the Fourier transform, but we'll be solving partial differential equations. We're going to take Fourier transform in the space variable. Okay, so I'll get started today, and I want to talk about the real Fourier transform before I do the complex version. They're going to be equivalent in the end. But it's easier, just like we did with Fourier series, to start out with the real. I'll call this Fourier integral. And this is a classic motivation that you'll find them in most books, especially engineering books. So here's the motivation. I'm going to think about what happens if I do a Fourier series on a big interval. And I'm going to take my function here to have what's called compact support. So it's going to be 0 way out far away, and then it's going to have some bumps maybe, and then it's going to be 0 again. Blast. Okay, it's 0. And then it's got a couple bumps, and then it's 0 again. That's going to be, this is my x direction, and this is f of x. So I'm going to make f of x is going to be C2 smooth and what's called compact support. Compact support. Okay, the support of F is the set, it's called SUPP. The support of F is equal to the closure as a set closure of the set where F is non-zero. Okay. It's the closure of the set X such that F of X is not equal to 0. And compact support would mean that's a closed and bounded set. So the support of F compact means this, well, it's closed because it's a closure, is closed, it always is, and bounded. Compact sets are closed and bounded. So it always is closed because it's defined to be the closure of something. So it just means the support is bounded. Okay, so then there's one in the picture. And so now the big idea is going to be, let's expand this thing in a Fourier series. Let's see, that's minus L to plus L. Okay, so the idea, we're going to write, expand f of x. We know it's C2 smooth, so the Fourier series is going to converge to f nicely. And so I'm going to expand it
I'll have here an. Remember when we did this for a non, when it was L was something different than pi, we got cosine n pi x over L here, plus Bn sine n pi x over L. And let's see, that's going to be, remember A naught is the average, 1 over 2L integral from minus L to L of f of t dt. That's A naught. And then we get plus, let's see, I'm going to mess around here a little bit. Leave me some space here. Sum, as n goes from 1 to infinity, of let's see, those Fourier coefficients, the ANs, are going to be 1 over L, integral from minus L to L of f of t cosine n pi t over L dt. That's the AN. That's the AN. And then I had here cosine n pi x over L. And then I'll have a very similar thing for the sine stuff. It's going to look very similar, so I'm not going to write it out. Okay, as L goes to, so now we're going to let L go to infinity. Well, that f function has compact support. So that integral there in the A naught term is going to be, that integral is going to be some finite area. And I'm dividing by 2L. So this goes to 0 as L goes to infinity. Since the support is compact. That integral of f stays the same at some point as L is bigger than the support. And so dividing by 1 over 2L makes it go to 0. All right, now this thing is, if you stare at it long enough, you think, my gosh, that looks like a Riemann sum. And so let's see, I'm going to make it more like a Riemann sum. I'll divide by a pi out in front. Make it a different color here. I'm going to 1 over pi goes here, and so I can put a pi over L. That looks like a delta something. I'm going to call this right here Wn. The T, without the T. Wn times t dt. Okay. And this thing looks like a delta W. Okay, so I claim that if you stare at this, this feels like a Riemann sum. It's a Riemann sum in the W's. Okay. Let's think about where the Riemann sum is going. The W's are those Wn's are n pi over L. So this would be 1 times pi over L, 2 times pi over L, 3 times pi over L, etc. And there's the delta W's there. And so if you think that this is going to go to summation as n goes from 1 to infinity. Let's see, I've got a 1 over pi to float along. But this is going to be, let's see. I'm going to let the L, because f has compact support, I can let that L go to infinity in that integral. So I'm going to have integral from minus infinity to infinity f of t cosine n pi over L t dt. And I can do this because f has compact support. I can replace L by infinity since f has compact support. It's 0 out there, so I'm not actually doing anything since f has compact support. Okay, so let's see. I'm getting close here. All right, so this was my omega, my Wn dt. And I have here a cosine Wn times x. And plus a similar thing with the sine stuff. Okay, and that's looking like a Riemann sum in the W stuff. Oh, where's my delta? I need to multiply the whole mess by delta W. Delta W. Okay, so I claim that this goes to, as L goes to infinity, to an integral from 0 to infinity, the function a of W times cosine Wx plus b of, I didn't write the sine stuff, but they're going to be very similar, Wx dW. Where the a of W is 1 over W, 1 over pi integral from minus infinity to infinity, f of t cosine Wt dt. So the t integrates out, and I'm left with a function of W. And b of W is a similar thing, but with sine in place of cosine. Okay. You can make this rigorous if you feel like you have to. So you can actually do epsilon deltas and show that this all converges. We're going to do a simpler way, sort of a more theoretical way of seeing it's true, kind of like we did with Fourier series. But this can be made rigorous. It really made me angry to sit through it and kind of not believe that it was rigorous when I was an engineering student. They didn't want to dwell on the theory. But a little bit of theory goes a long way in understanding this stuff. And we're going to do it in a fancier, more modern way, like Stein does it. Okay, so this was just motivation of why we're going to get these formulas and why we might suspect that they're going to be true. And let me explain why that's an exciting formula. You see that so let me summarize what I've got here. I'm going to have f of x is expanded in a Fourier integral. So it's going to be an integral from 0 to infinity of, notice this kind of looks like a Fourier series. dw. Where, I guess I just wrote this, a of w is 1 over pi integral from minus infinity to infinity of f of t cosine wt dt. And the b of w is the same thing, but with sine. So here's what we think of. So this is the Fourier integral. And if you think of a Riemann sum there in the w's, you realize I'm expanding f in terms of all frequencies of cosines and sines. So the feeling f of x equals limit of a Riemann sum and if you think of that, a Riemann sum in the w's, those would be cosines and sines of all frequencies. And the w's are positive, so that integral goes from 0 to infinity. So it's going to be a limit of linear combinations, limit of linear combinations of sine and cosine in all frequencies. Cosine wx, sine wx, as w ranges over all positive frequencies. Okay, it's a limit of Riemann sums. And so that's kind of like Fourier series, because Fourier series, we had 2 pi periodic things, and we expanded them in terms of the basic frequencies of music. So Fourier series f of x 2 pi periodic can be expanded as a linear combination of the musical frequencies. That's what I like to think of them as. The musical, the ones that come up when you solve the string problem. Musical frequencies. Cosine n pi x, no, cosine nx sine nx. Okay, so it's exciting if you're doing electrical engineering and you want to expand a function that's not 2 pi periodic in terms of all frequencies. And that's